everyone. That fanfare in and out of our lovely presentations never gets old, does it? Never gets old. Ladies and gentlemen, welcome to another edition of Patio Productions, where we pre-calculus from the patio. We have actually arrived on our very last section for chapter 13, and I am super excited to share this with you guys. It's a little bit of some preview stuff that we get to use in calculus if you are actually going on to that class, which I'm super excited. So you will be seeing this stuff again. And so let's just jump right in and get started. So here we go. Let's get this PowerPoint pulled up. Come on, Mr. PowerPoint. Okay. So for our subject today, we're going to do something called a power series, right? So like power series. Okay, I think power series is something that is quite lovely and quite fantastic, and actually is how your calculator works, which is like so amazing. And so we're going to talk about doing a series, but then we're going to talk about this thing called like a power series. So you're like, Mrs. Fox, what is this? I'm so intrigued. What is happening? So what you want to really think about, guys, is this is actually talking about a series, okay? Now, when we talk about our series, this other word was in front of it, right? So a power series. So what's going to happen is we're going to have a series of numbers that have like a cute pattern to them, but each guy is going to have like a variable to it that goes in increasing powers. It's actually like really cool, really fantastic. And so I'm super excited to jump right in. Did you guys print out the note paper for today? I just think it's going to help make taking. Those are not even words. That's not even a sentence. Oh my goodness, you guys. Let me try this again. It's going to help us take notes in an organized fashion, and you don't have to write down so many things. So it's a little bit just kind of like I printed out the slides, but I really think it's going to help you guys. So hopefully you went ahead and found that baby and you have printed that out. So a quick little disclaimer, guys. The notation here is going to be, it's going to be very mathy. It is, okay? We're going to have mathy notation, and I do not want you guys to be afraid of it, okay? It's going to be amazing, and so you're just going to have to accept it, love it, really embrace it. It's got sigmas and powers, and it's going to look beautiful, and just really like focus in on the invitation, because like we got our massive powers, and I know you guys can do it, okay? So if we have a polynomial, polynomials are actually pretty simple to calculate, and you could either do them like in your head, or you could do them on a calculator, like a very simple calculator, like even like a 4-function calculator, and you would be able to do it. And so I just want to know, like, do you guys know how to do like complicated things like quote by hand? I mean, like, I don't, right? Like, I know, like if you told me to go ahead and calculate cosine of something that was not a famous angle, I'd be like this, I don't know how to do that. But a power series would actually allow us to go ahead and calculate something kind of complicated by just using a series, okay? Now, the way that these series are developed are actually proved in calculus. We actually develop them, not just like look at them and memorize them, but this is pre-calculus, right? Of course it's pre-calculus. And so when we do our pre-calculus, we're just going to be exposed to them and use them, but not really talk about where they come from, okay? But they do come from somewhere kind of amazing. So a power series, okay, is actually the sum of a sequence with increasing powers of x, right? So there is like this idea of a sequence, so a pattern of terms, and then increasing powers of x. I have now introduced a variable into the mix. Again, please do not be scared by the notation, okay? So we are going to have a pattern to the numbers in the front. I want you to look at this right here. So this says a naught or a sub 0. You actually say the word a naught, like an OT. Okay, so a naught plus a sub 1. And then if you jump to here, there's an a sub 2 and an a sub 3. And then as we go up in our terms, so this is like the very first term that we start with, the 0 term. The first term has an x to the first power. The second term has an x to the second power. The third term has an x to the third power. So do you see how we are increasing our powers of x every time we go to a new term? Okay, so what this means is that this is interpreted into the sigma notation, okay? And our sigma notation, yeah, so gorgeous, okay, says we're going to take sigma from k equals 0 to infinity. So we're going to start with the 0 term and then go to infinity. And we're going to have some sort of a coefficient in the front, so a sub k, and then x to the k power. This is just a coefficient and going to have a pattern to it. This right here is just saying we're taking increasing powers of x. We're not freaked out. Okay, in the next box, I want you to write a couple of things down. So I want you to notice that k starts at 0 to allow a general term, right? Just a general term in the front, like a 1 or a 2, or just like a regular number in the front, okay? Another thing we want to put down in that box, that middle box on our note paper, is that the coefficients are not necessarily going to be the same thing. There could be a pattern to the coefficients. Maybe it's like 1 over n. So it'd be like 1 and then 1/2 and then 1/3 and then 1/4. Maybe it's something even more complicated than that, or maybe they are the same. It just depends, okay? So if the numbers are the same, okay, then this a term right here is going to actually be a geometric series, okay? So if we have all of the a's being the same, okay? So the a's are, I can't even write that. Okay, forget it. Nope, I'm gonna veto that nonsense that I just did right there, okay? So if the a's are the same, then yes, ladies and gentlemen, you just get a geometric series, and we're going to work with that a little bit today, okay? And so let's write down in that last box on our paper what it would look like to be a geometric series. So to be a geometric series, we're going to have the summation from k equals 0 to infinity of a times x to the k. And then notice that it doesn't have any sub numbers on the a because every single term has the same a, okay? But the x's are basically what we're multiplying by. X is our common ratio, and we just get increasing powers of them as we go, okay? So it would be a, and then we would have a plus a times k x to the first, plus a times x squared, plus a times x cubed, plus ... Okay? So basically this whole section, we have been interested in things that converge and diverge. So I want to know, like, what's going to make this stuff converge, okay? So what values of x would make this series converge? So if you look, this is not saying that there is a pattern to our a's. They're saying every a is going to be the number 2. Okay. That means they're all the same. That means it's geometric. Yes, good work, guys. It is geometric. And so if I were to write out some of these terms, I would say the summation from k equals 0 to infinity of 2 times x to the k is going to be 2 plus 2 times x, which is to the first power, plus 2 times x squared, plus 2 times x cubed, right? We're just going up, increasing powers of x. And so what that means is that it is for sure geometric. I'm super excited. Your first term is 2. Yeah, I see it right here. Guys, look right here. It says that 2 is my first term. Nailed it. Okay. And my common ratio is x. Folks, that is in fact what I'm multiplying by each time, okay? Now, what makes things converge and diverge when we have geometric series? I feel like I just did that like a day ago, right? Like, seriously, although the days are sort of blending together, I don't really know when I did that lesson or when you did that lesson, but let's say it's, in our recent memories, okay? We know that if the absolute value of our common ratio is less than 1, then it will work. So that's what I'm going to say. My common ratio this time is x. So if the absolute value of x is less than 1, then these values will converge. Folks, this means that you can split this up into like a number sandwich. That's what I like to call it, a number sandwich, okay? And so you know that if the absolute value of x is less than 1, the two numbers that it would have to be between are a -1 and a +1, and that is going to be our official answer right there. So you go ahead and you split up that number lines, Mrs. Fox, that's not the right thing. You split up the absolute value into its negative version and positive version. We know when we do our negative version that the sign would have to flip, and that's why you get this beautiful sort of like number sandwich of the values that will make it converge. Okay, so what will it converge to? Oh, that's when we use the geometric sum formula. The geometric sum formula says that you're supposed to take a sub 1 for the top and then over 1 minus the common ratio. Folks, that is the answer that we would put, okay? So in general, okay, we are going to say that for any constant a, the infinite geometric series is going to converge to this. Well, yeah, that makes perfect sense, Mrs. Fox. That's the formula for an infinite geometric sum. If, right, only if the absolute value of x is less than 1. If our absolute value of x is greater than 1, then you're like, not going to converge. It is in fact going to diverge. Next, a little note I want you to write down for yourself, and this is a vocabulary thing, okay? So when you see this in a calculus class, you're not going to be freaked out. You're going to be like, oh, I have this vague memory about learning something like that, okay? If you say that the absolute value of x is less than 1, we turn it into the number sandwich of -1 is less than x is less than 1, and it's called our interval of convergence. Okay, interval of convergence is just, the interval on what values it's going to work for. Interval of convergence. Okay, let's get ourselves a new page. I decided to change my page turning to a different sound. Here's the page turn sound. That's so fun. And we're going to try example number 2. So this says, find the power series that will converge to this sum. Oh, okay. So what they've done is they've given us the answer. Oh, okay. Well, let me just undo that right there. Hold on a second. Okay. So they've given us the answer, you guys. So if this is the answer, okay, don't we know the things that happened? This term right here was our first term. This guy right here was our common ratio. Folks, I think I'm just going to take those two pieces of information and plug that into our summation notation. So again, that's our a sub 1 term. That's our r term. Okay, this would mean, now this looks scary. You're like, what is happening to this information? This looks scary. No. It's not scary. It's not scary. You guys got this. Okay, you guys got this. It's not a big deal. You are going to think to yourself, all right, maybe I even write this part first. In fact, that's what I think I'm going to do. I'm going to write this part first. I'm going to go summation from k equals 0 to infinity of the a guy, 5, times the r guy, which would be the 1/2 x to the k power. Well, look at that. Then I think what I'm going to do is I'm going to write out some of the terms. So then I would write out some of the terms. I start by plugging in a 0, and the first term's just 5. Then I'm going to have a 5, and then I'm going to have the r, 1/2 x to the first power. And then I'm going to have the 5, and then the 1/2 x to the second power. And then a 5, and then a 1/2 x to the third power. And that's what you're going to do little bit by little bit. I really, truly think that if you start with this stuff, it's a little bit more confusing. So again, please start by writing in a notation first and then write yourself out some of these terms. I think that'll be much smoother. Okay. When does it converge? Oh, okay. Well, this would be our R value, right? And so we take our R value, we put it in absolute value, and we say it has to be less than 1. We make our number sandwich. Our number sandwich is going to say from -1 is less than 1/2 x is less than 1. Now, self x is not by itself. No. I need to figure out a way to get x by itself. So how would I get x by itself? You're going to multiply by 2. But guys, there's kind of like 3 parts to this like little inequality. And so you need to do multiply by 2 to all the 3 different parts. If you multiply by 2 on all the parts, you get -2 is less than x is less than 2. And folks, that is your interval of convergence. Isn't that nice? So, did you fall asleep right now? Did you fall asleep? Oh my goodness. Guys, I pushed the wrong button. Oh, so silly. I hope you didn't fall asleep during that example because that was you. I apologize. So, yeah, guess my patio, Foxy over there in the corner is getting a little tired of these lessons. Oh my goodness, so silly. He doesn't have a name, by the way. We tried to name him, but I'm not sure what his name is. So if you can figure out a name for Foxy back there, I mean, he is my only student. So send me some suggestions, would you guys? That'd be super exciting. Okay, we are back to the lesson. Okay, this says find the interval of convergence for this beautiful guy right here. So you're thinking to yourself, okay, self, this really is just a power series. Now, why is it a power series? Ladies and gentlemen, if you think about this guy right there, where's my little mousey guy? Oh, here it is. Okay, we are taking x plus 2 and we're raising it to a new power each time, to the first, to the second, to the third. So guys, that's what my common ratio is. I am taking, okay, an x plus 2 and raising it to all of the powers. Okay, Mrs. Fox, I see how that works. I can also see that our first term is just the 1. And in fact, there's a 1 in front of each one of these guys. So it is totally like a geometric series. So I think I'm just going to take that the R of x plus 2, put it in absolute value bars, and make it be less than 1. Okay, yeah. I see how this works. So cool, so cool. We're going to put the number sandwich, and we're going to make the -1 is less than x plus 2 is less than 1. And then on the previous example, what we ended up doing up here is multiplying by 2 to get x by itself. On this one, I think that we're going to subtract 2 from all of these, right? Because that would be a way to isolate this. So I subtract 2 from all 3 of the parts. And when I subtract 2 from all of them, right? So on this one, I'm going to subtract 2. And this one, I'm going to subtract 2. And on this one, I'm going to subtract 2. These cancel. We simplify. And I get -3 is less than x is less than -1. And that is my interval of convergence. Love it. So good. I think we should definitely applause for that one. Excellent work, everybody. Okay, all 3 of the examples that we've done so far have been like a regular, like rational function, right? Something that we could write as like that sum notation with the first term over 1 minus r. But we can also do other kinds of functions like I was alluding to at the very beginning of the lesson. And so we can do actually, there are some functions that have very, very cool power series. Okay, these 3 that we're going to talk about today, and we are going to write all 3 of these now, are e to the x, sine of x, and cosine of x. And it is actually how your calculator works. Like, it's kind of impressive. And so I feel like maybe I should just do the fanfare music for it, right? Because truly, this is amazing things, okay? E to the x is something crazy. I don't even know how to calculate that. Sine of x, cosine of x, crazy things. But I can actually do them by hand. It's the craziest thing ever, you guys. This is what algorithm is stored in your calculator and what makes your calculator work. Don't you feel really smart right now? Like, ooh, smarty McSmarties that we can do this. So here's the deal. For now, we're just going to use them. We're just using them, okay? Oh my goodness, there's a change on your note paper. On your note paper, it says memorize. Scratch that word out. Gone. And I want you to change that to use them, okay? So we're just going to use them right now. In fact, if we were going to take a test or a quiz on this, I would show you the power series and say, here it is. Now go use it, okay? Because you don't really know where it comes from until we use this thing called a derivative in calculus. We are so not there. So we are going to just use these power series. So let's write down all of them. Again, please do not be afraid of the notation. This is a beautiful series, and we're just going to think about the pattern. So let's copy it down. Okay, the first guy right here for e to the x. The power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... because it is infinite. This right here is our general term plus x to the k over k factorial plus ... This is insinuating that we're going on forever. In beautiful summation notation, it is the sum from k equals 0 to infinity of x to the k over k factorial. In fact, just rewriting this general term over here is exactly what you do for the power series. The sine of x1, okay? This one looks a little bit more scary. No. We're not scared, right? Let's just use our superpowers. Be all amazing about this and just look for patterns, okay? So here's the deal. I'm going to go over here to this general term first, just to kind of like explain what's happening, and then we'll write out some of the terms, okay? This is saying it's the summation. So let's put your eyes over here. Put your eyes over here. Stop writing over here. No. Don't write. Okay? Be over here. So this is saying that we're going to take the summation from k equals 0 to infinity of -1 to the k. What this -1 to the k is right here is asking us to do alternating numbers, right? Alternating positive, negative, positive, negative. We're going to have x to the 2k plus 1 and then over 2k plus 1 factorial. Notice these are in parentheses. Folks, this is just saying odd numbers and odd numbers, okay? So we're going to do alternating powers, starting with positive, then negative, then positive, then negative. And then it's x to the odd powers over your odd numbers factorial. That's all it is, okay? How does Mrs. Fox remember this? She kind of does like a cute little thing in her head. She remembers from earlier in the course that sine of x is what we call an odd function. Do you remember that? So because sine of x is an odd function, I've kind of like committed that to long-term memory. And then I think to myself, oh, I'll just say that sine of x is the odd numbers. Clever, right? Don't you think? Yeah, I think so too. So let's write out some of these terms. So sine of x is going to be x minus, because this is a positive, x cubed over 3 factorial. Then we go to plus x to the 5th over 5 factorial. Back to minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. The next one would be a minus. We put plus dot plus the general term, which we already wrote down from over here. It's a -1 to the k times x to the 2k plus 1 all over the quantity 2k plus 1 squared plus dot. So maybe you now could just like take a guess at something, right? So sine of x happened to have using the odd numbers, okay? So sine of x was using the odd numbers. It alternated signs. We did some factorials and we did some powers of x. Now, take a guess. What might cosine be? It's the even numbers. You guessed it. Good job, guys. Excellent work. Okay, so again, let's go over here to the general term first before we try to look at the specifics, because sometimes the specifics can be overwhelming. It is, again, going to be the summation from k equals 0 to infinity. We're still going to do -1 to the k power. We are going to have alternating signs. Starts with positive, then negative, then positive, then negative. And then we're going to have x to the 2k and then 2k factorial. Notice that this 2k is in parentheses. 2k is just going to now get us the even numbers, okay? So for Mrs. Fox, she thinks in her head that cosine is, in fact, an even function, and then it's really easy for her to remember how to do the cosine power series. So why is there, I honestly think this right here is the most confusing part. Why is there a 1 right here? Okay, well, this is a 1 because it's an x to the 0 power first. Yep, x to the 0 power. So x to the 0 power would be 1, and then 0 factorial is actually also 1, okay? So the first term has no x's but a singular 1, and I know what you're thinking, Mrs. Fox, 1 is an odd number. No, that's not what you're thinking. Okay, don't think like that. Think to yourself, it's just going to be x to the 0 power over 0 factorial, which simplifies to be a 1, okay? So then it goes minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, noticing that is switching signs every single time, and we only have the even numbers. Minus dot plus the general term, which we already talked about, -1 to the k, x to the 2k over 2k factorial plus dot. Okay? These are, in fact, the algorithms that are stored in your calculator, and then we can actually do these by hand. This is like the coolest thing ever. Okay? Here is go to the next page sign, and let's go ahead and do this. So example number 4, we're just going to do a couple of examples here. This is kind of a longer lesson. Sorry, guys, right? I know, but it's like just such meaty stuff we have to get in here. It says use the first 7 terms of e to the x to calculate e squared and then compare it to your calculator's answer for e squared. Okay, so here's what we're going to do. The first 7 terms, okay, if you go back into your notes, so if I go back to this slide right here, these are the terms, right, for e. E goes up in powers, everything's positive, and then the factorials on the bottom are just like regular factorials. Okay, so this is our power series, and we're going to write the first 7 terms. But every time we see an x, we're going to write a 2, right? Yeah, because we're trying to find e squared. So the first term is a 1. Then there's just x, so I write 2. Then it's supposed to be x squared over 2 factorial, so I write 2 squared over 2 factorial. And then I just keep going. Plus 2 to the 3rd over 3 factorial, plus 2 to the 4th over 4 factorial, plus 2 to the 5th over 5 factorial, plus 2 to the 6th over 6 factorial. That is, in fact, 7 terms. 1, 2, 3, 4, 5, 6, 7. Nailed it. Okay. I'm going to put all of this in my calculator. I'm going to use some parentheses. I'm going to do all sorts of beautiful things to figure out what this is in my calculator. So I'm going to give you 2 drum rolls to figure it out in your calculator. Go. Maybe that was enough time, maybe not. Pause it if you need to, but here's our answer of 7.3556. I'm sure that's rounded a little bit. Okay, so here's the deal. I want you now to just scrap that and now just put in your calculator e squared, okay? E squared and hit enter. Ladies and gentlemen, it's about 7.3891. Ladies and gentlemen, I cannot even believe this, right? We were actually able to get something that was really pretty close. In fact, if you had like rounded this to the nearest 10th, it would have been the same answer. Okay, these are within 0.4 hundredths of each other, which is like the coolest thing ever. Now, if I wanted this to be more accurate, I actually just use more terms. Okay, the more terms I use, the more accurate it would be, which is just kind of amazing. All right. We have one more thing that we want to do, just a very cool little extra piece, okay? If we were to let the numbers in your series be imaginary numbers like ix as opposed to just regular x, we get this kind of amazing thing. Like I can't even believe how amazing this is. I'm just going to do the whistle because it's kind of cool. So if we are able to take your power series and plug in I times X for every one, you will get a combination of the cosine guy and the sine guy with an I being multiplied by the sine. Okay, we're not going to take the time to actually do it out. I just kind of need to show you that it happens. Okay, and then do you remember that cosine X plus I sine X in polar? Do you remember that in polar that was like cis, that was your cis notation. Okay, so what we're going to do is we're going to actually just do a little bit of a combo of like trying to transfer something to another thing. It's actually kind of smooth. Okay, but what happens is because this guy of the cis part right here, the cosine X plus I sine X is the same thing as e to the I sine X. We're just going to like replace all of this right here with the e notation and slap the R in the front. It's kind of cool. So we're just going to do one of these, and literally, I think by one example, right now you're like a little befuddled. Your brain's doing this. No biggie. Let's do an example because it's always better when you do an example, okay? So this is example number 5. It says we're going to express this complex number in this E notation. Okay, so the complex number in the E notation. So here's a complex number, rad 3 plus I, or like 1I, and we're going to change it into this. Now, when we were in polar unit, we were able to change this into cis notation, right, where we found the R and we found like the theta. So we're going to do something very similar to that, okay? Very, very, very similar. So if you're having like a little deja vu moment, like it's appropriate. Don't even stress. Okay, so first thing we're going to find is the modulus, which is our R. Remember when we did R, you do the Pythagorean theorem with your components, your A and your B guy, or your X and your Y guy. So we're going to take rad 3 quantity squared, and then we're going to add 1 squared. That becomes 3 plus 1, which is 4, and rad 4 is 2. Okay, so the R number is going to be 2. Got it. Our argument is the angle, okay? So let's think to ourselves. Can we just maybe draw a picture? I think I'm just going to draw a picture. Like, I'm going to go over here. I hope this is not on top of something else. Folks, if the x value is rad 3, but the y value is a 1, right? So if this is rad 3 right here, I'm doing it with this mouse, so it's horrible. This is 1 and this is 2. Can you guys just sort of look at that and be like, oh, you like that picture? Thanks, guys. I thought it was not so bad myself. Isn't this just basically like a 30-degree angle, like a pi over 6? Okay, so in polar form, right, we would go like this. We would say that this turns into, I think, okay, sorry, let me go backwards. In polar form, it would be like this. Like it would be 2 and then cis, right? Like this would be our cis notation, pi over 6. Cosine of pi over 6 plus I sine pi over 6. So what we're saying this time, guys, is we're going to change this polar, this cis part right here, right? So this is like 2 cis pi over 6, and we're going to change that into the E notation, where literally all you're going to do is take the angle and write it in the power. And so it looks like this. 2 times E to the I pi over 6. That's it. That's all there is to it. That's your answer, okay? So you are literally doing an old school question, a polar, like going from the complex to the polar complex, and you're just changing one itsy bitsy little step to the side, and you're just going to take the modulus out front and then write E to the I and then whatever the angle is, and that's it. That's how we do it, ladies and gentlemen. This is going to be your assignment, okay? You're going to practice all the things. And so all of this is new to you. So I want you to just be like, nope, I got this, okay? You're going to exercise your like pre-calc superpowers. You're going to be like, I got this. I'm going to look at the notes. I'm going to look at the examples. And I'm going to feel good about this. All right, ladies and gents, we are going to go ahead and see my face just one more time. Oh, yeah, I miss you guys. I miss seeing you. I hope that seeing my cute little face, right, is bringing you joy and maybe not sadness. Sadness? No, not sadness. Only joy and just like this. Ta-da! Okay, so guys, have fun with your last section for this unit. For our next lessons, we're going to do a little bit of review because I felt like maybe as you've been doing this stuff, it's been pretty good, like day to day to day to day. But then what if we like try to put it all together? Is that going to be too hard for you guys? No. We're going to practice it. Okay, so we're going to practice putting some things together. I think next week we're going to do a couple little reviews, and then we'll do like the group quiz, and then we'll figure out a way to finish all this up. Okay, guys, I miss you. I hope you're staying safe out there. I think that's it. All right, fanfare music to end. Bye, guys. See ya. Bye.